Let us see how Euclid says we should solve a problem like this, solving an equation. So here we are given AB and BC, two straight lines. What we have to do is figure out K so that this equation is satisfied. So let's see how we can proceed. So let's take the right hand side. BC square. So first thing we do is we draw a square on BC. And let's mark these points as D and E. Now this square has to be divided by 4. So to divide it by 4, we take the midpoint of BC and we draw a square on BF. So which means that this green square is equal to BC square by 4. Again, let's mark these points. Now we draw a semicircle on AB and we draw a line GH. We extend it and take the intersection with this semicircle as J. Now let's join J and H. Now from J, we draw a line perpendicular to AB and we take the intersection with the line AB as K. So we have found K, which is what we had to find. Let's take it a little bit further to understand what is happening. What we are going to do is we are going to cut off this line JK such that KN is equal to KB and we will complete this rectangle. Let's name this point as L and we will complete the parallelogram on KB, which will be a square, BK square. And let's mark this point as M. So here AB times BK is nothing but AB times BM, because BK and BM are equal to each other because it's a square. So AB times BK is this entire rectangle minus this square will give us AB times BK minus BK square, which is the remaining purple rectangle. Now here we are saying that the area of this rectangle will be equal to this square, green square. So we have found the point K on AB, or rather AB has been factored into two line segments such that this equation is satisfied. So now let's see what's happening. AB times BM, BK is equal to BM because it is a square, minus BK square equal to BF square, because BC square by 4 is equal to BF square. Or in other words, we can say AB by BM is AM rectangle. So AM minus BK square, that is KM, is equal to the square on BM, that is BG. Now let's look at it numerically. AB is equal to 10, BC is equal to 8, and BC square by 4 is equal to 16, because remember BC is 8, so the square is 64, and we have divided this 64 by 4, so we get 16. AK is equal to 8, BK is equal to 2. AK times BK is equal to 16. AK times BK, 8 times 2 is 16, which is equal to BC square by 4, which is also 16. And AK plus BK, AK plus BK is equal to 10, which is equal to AB. So in one of our previous sessions, we saw how to factorize, right? Factorization we saw. So we are utilizing that factorization to solve this equation. So now in modern notation, how does it look like? So let me hide this square so that we can see it properly. In modern notation, if AB is equal to A, BK is equal to B, and BC is equal to C, then AB times BK becomes A times B minus BK square, that is B square, is equal to BC square by 4, that is C square by 4. And if we want to remove this 4, we multiply entire thing by 4. So 4AB minus 4B square is equal to C square. And if we take all the terms on the same side, we get 4B square minus 4AB plus C square is equal to 0. The thing is, if you draw it carefully, then you can change the length of AB and BC. So I'm increasing BC now. Okay. So for example, if AB equal to 10 and BC equal to 7, then you get into decimals. AK will be 8.57, BK will be equal to 1.43. BC square by 4 will be 12.25. The solutions will be correct. Of course, I'm doing a little bit of uh, rounding here because otherwise it gives 10, 12 digits of decimal places. Now, if we get something like this, it becomes difficult to find the factors. Factorizations become difficult when we have such numbers. Whereas if we do it geometrically like this, it doesn't matter what the length of AB and BC are. We will always get the exact value of AK and BK. That is solving equations using Euclid's method. That's it for now.